All right, welcome. So this is not the Julia Dispatch podcast, but this is something that we're going to try out new that we'll be throwing onto the Julia Link channels. There's a lot of people who ask about what goes on in developing behind the scenes. And I thought that it would be nice to kind of pull some developers out and just have a dev chat, right? So this is something that we're calling the SciML Dev Chat. Hopefully we can do more episodes of this. Basically, the idea is it takes a lot of time to write a blog post about everything that's going on inside of all the development work. And so why not just pull everyone into a little studio here and just talk it out for an hour? All we have to do is write down, a bunch of different topics that are the main topics going on, and then focus on them for this discussion. So for this discussion, I want to focus on 4 different topics. One is trimming support throughout SciML. The other topic is base splitting refactors. So if you've seen a bit of instability about some things going on in SciML, what's been going on there? What are we aiming for? When is this done? When is this end? Right. I think that really highlighting that is a good thing to mention. And then everything going on with the SymbolicUtils rewrite, basically the stuff around making ModelingToolkit precompile well. And finally, if we have time for it, the breaking changes that we're aiming for in DifferentialEquations.jl, the upcoming differential equations VA. Right. So we want to kind of hit these topics and just kind of walk through everything that's going on. So, who are we? I'm Chris Rackauckas, right? So I'm the BDFL of the SciML space. I've been here in the Julia space for a while. So folks might not know me, but you might not know some of the other developers on here. So let me, Oscar, you might want to introduce yourself.
Hi, I'm Oscar. I work for Julia Hub, and as my title, and this says basically work most of the time on making sure the numbers are doing the right things.
Yeah, so I think if people don't know a lot of Oscar's work, a lot of things like what is it, like the base implementation of log, the base implementation of exponent, like a lot of like detailed numerics work, all comes from Oscar going around, right? So Oscar has also been doing a lot in the SciML space, and you'll hear about some of his contributions in extending what the kind of level of robustness that he kind of works on all the way up through the ecosystem. Then also we got Aayush as well.
Hi, yeah. So I'm Aayush. I also work for Julia Hub, and most of my work centers around the symbolic numeric aspects of things. So if you've touched Modeling Toolkit in the past year or so, you've probably seen me around there. And so I generally work with the Modeling Toolkit and symbolics and SymbolicUtils and the stuff that all of that touches.
Alrighty. So yeah, so that's everyone involved. So let's just go to the first topic here. So the first topic is everything to go around static support and trim. Right. I just want to kind of show something. Let me see how easy it is to just go in right into screen share. Right. So I think the thing that kicked a lot of this off. I want to do a big shout out here to Romeo, who showed up at the JuliaCon hackathon, or the hackathon in the summer, right, and just said, "I want to get Julia C and trimming working on SciML," and we're like, "All right." And he kind of forced it to work. But when we say we forced it to work, there's a lot of things that had to happen there. So, maybe
there are about 10 dev packages. Yeah, you have to use a very specific algorithm. Right. Yeah, you have to use the right branches of everything.
Have to use the right branches of everything. Yeah. So when we say we got it to work at the hackathon, we mean no mere mortal could get it to work, right? But with the right combination of with the right combinations of love and support, you could get a version, right? But then since then, the goal has been to make that be a normal standard supported thing, right? So Oscar, I know that you did a few things related to base and a lot of these things. You might want to walk through some of those.
I've actually stayed mostly out of the base side of trimming. Gabriel and Cody have been mostly keeping that up. But essentially, all of the things that we've had to do to make this work, there's a number of spots in base that aren't trimmable, but only on an error path. And so there's had to be a bunch of work to make it so that you can either make it so that trimming will work, but the program aborts if it hits one of the errors, or make it so that the errors are better understood. Because in regular Julia, it's often worth going through some dynamic behavior when you need an error, because the error is the slow path. And so you don't want to compile necessarily all of the code to do that right away. So you have to undo a couple of those heuristics to make trimming work properly.
We then had to build a lot on that. I mean, one of the biggest issues with trimming for a while was actually just getting linear solve supported, right?
Right.
So yeah, there's a bunch of junk in here that you might see now, like at static this, right? Where using if you saw that there were some version bumps in there, where you're just like, oh, now I get a little warning about a precompile error, because we there were a lot of things that had to be shoved around to make it so that way we satisfied the constraints of static compilation, which at this point aren't really so documented, but I guess now you can use a linear solve as your shining example of how to do extensions with with loading binaries and everything with the Julia C support, because I found it out by example.
Basically what the rule is that you have to be able to tell ahead of time what algorithm you're going to use. Because if you don't know ahead of time what algorithm you're going to use, you have to compile the code for all of the algorithms. And some of those algorithms might not work on your system. So, like, for example, if you have if you dynamically might pick CUDA as one of your algorithms, but you don't have an NVIDIA GPU, that's going to be a problem. So you want to make sure that those choices are made statically based on system rather than based on the system dynamically.
Well, and one of the things that we had before is we just say, use CUDA is CUDA.functional, right? So you say, oh yeah, ask the CUDA library if you're allowed to use it, right? It turns out like a lot of these things and the binary build stuff are not actually static.
Might need to move some of this further up to static.
Yeah. Well, I mean, yeah. So what we had to do is we just had to create these functions that was just like, oh, it's always false. And then it's like, if you trigger the extension, then it would actually do one of these things. It's like, oh, as long as you're not trying to build with CUDA, then you're static here, right? So a lot of these little things, I think some people might have seen like the warnings, like, we had a version in there where we just didn't do the nothing part, right? And so it overwrote the same thing, right? And so there's like a precompile. This is what all that kind of movement was. But I think we got most of it figured out. Except when I say most of it, there's still one major piece here, right? And I think that Aayush, your part here, right?
Yeah. So I think the major piece there is essentially just one little function in SciML base that doesn't want to trip. And well, actually, so with that PR, this PR, it does trim. The main issue to work through there is being able to test it, because down the line we might make a change that suddenly breaks trimming, and we want to know when that happens. So it's a matter of getting Jet to cooperate on 1.12, or like finding another way to test it where we don't run into the same issues.
I have good news. As of like a week ago, I think Jet works on 1.12 now.
Oh, hey.
Does it?
Yeah, I'm pretty sure we fixed that.
There was one piece here, which is that, there was this this issue that we opened during the hackathon, which is that Jet did give false positives on some of the things that we're looking at during trimming, or false negatives.
Yeah, that's the exact one that we run into with testing SciML base.
What Romeo was putting together was, and again, major shout out to him for kind of piecing a lot of this together. He put together this trim test in nonlinearsolve.jl, which is actually just putting together like a whole library to trim, and then in a separate process actually running the Julia C trim and then testing out the binary that's created. Right, so it's actually running this full thing. But at this point, we don't we need to create a reproducible script or something that does this, because putting this in every single library is going to be nasty if we have to try to do that.
Yeah.
Right. But at least we got this PR that does one, nonlinear solve, which is a decent amount of SciML. It covers a decent portion of it, right? So, but making it so that way we can just copy paste and put a trim test in every library. Either got to hope that Jet gives us true positives, or is really true about that, right? Because it has a now static analysis mode that says, right, this is trimmable or something, right? So that needs to actually be that needs to be improved, or we need to find some way to actually run the binary build in every repo and make this, because I definitely don't want to do what Romeo did here in every library. Otherwise, this is going to take like 2 or 3 weeks to set up just a bunch of trimming tests.
I guess then one way to test this would just be to run the trimming test from SciML base, and we don't run into any Jet weirdness. We just if trim passes, we're happy.
Yeah, we could have it just call we could just merge the nonlinear solve one now and just say, hey, look, now call the nonlinear solve.jl libraries trim test.
Yeah.
And then use that as a downstream integration. That gets us all the way up to nonlinear solver. And we'll need to write one for the ODE solver as well, which I guess, Oscar, you just told me right before we went on here that you got a version of at least the Rosenbrox to be.
Yeah. So explicit solvers, so SIT 5, Vern 7, those are really easy. They basically just worked out of the box. The semi-implicit was a little bit trickier because you needed linear solve to trim, so you need to do all the same things nonlinear solve does. The only other part that's a little bit tricky is your initialization algorithms. So when you have ODEs with algebraic equations, you need to figure out how to initialize those equations correctly.
Well, the initialization just is nonlinear solve, though, right? So if we solve this, that should.
So yes and no. There's a couple issues there. Issue number one is that if you're going from MTK, there's the MTK initialization, custom initialization, and that very much does not trim. The second issue is if you're using one of the normal or the Brownful basic initialization or Champagne collocation initialization, then
that goes to the OrdinaryDiffEq one.
Linear solve that trims. But in order for this to work, we need nonlinear solve with the default fully robust algorithm to trim, because this is only getting the some of the simpler nonlinear solve algorithms to trim. And whereas for this, you would need all of them to trim, basically.
You could set the algorithm and yeah, but I guess we'll need to get the full robust one to be trimmed.
What you can do, however, is one of the strategies for initializing is checking it, and checking it. Make sure that you've initialized it properly and throws an error, and that's the version that works, I believe.
Yeah, so you can initialize and then build your a real initialization point into the binary that you're putting in. Yeah, cool. Yeah. I guess one other thing, one last thing to highlight with all this, right, is that there's in order to make this all work, there was a pretty decently sized change to CPU summary.jl, right, which was CPU summary.jl to make it trim compatible. We've turned it into a preferences.jl version where instead of being all runtime triggers that then just evals the properties in, right, it's preference based now, which so what is CPU summary? It's the bottom library to things like loop vectorization.jl and finding out all the details about your CPU, and then so that way everything can statically specialize on it, right? The way that it worked before is that during init time, it would eval in what all the constants are, like, oh, what is the size of your L1 cache, or how many cores do you have, and all this, right? Now I have moved it to a preferences-based form, but some folks are a little bit unhappy about that, just because in the preferences-based form, you can set the preference directly, so that way it doesn't match your actual CPU. But B, this means that if you build a binary from this, it's going to make the assumption that whatever computer you're running the binary on matches the properties of the computer that you ran it on, right? Whereas before, this would dynamically statically set everything in your new Julia session, right, based off of the CPU that you're running on. So it's like loop vectorization.jl, completely static in the way that it runs, but it has a dynamic phase before it's all static, where it says, okay, but let me set everything up for the compile setup to your computer. There's actually a pretty major win in terms of precompilation and everything and the entire loop vectorization stack and all, but it means that your binaries are not relocatable to a new CPU. And that was one thing that I'm still talking about with Cody, just to see if we can get a better solution here. But this was a requirement to make anything trim. Yeah.
In the long run, our goal from the compiler team side of this is we do want to get rid of CPU summaries.jl entirely and replace it with some inference-backed mechanism that lets you do this sort of static dynamic thing. It's a fairly tricky problem, which is why we haven't done it yet. But in the long run, that would be nice.
This is a solution that most people would never notice like that it has this potential issue. But once we start redistributing binaries, if you distribute a binary to someone else that is using, loop vectorization.jl, it'll specialize in the cores of the computer that you built that binary on, not on the number of cores of that computer that they're running it on. And that is just something to know about with the current state of the ecosystem here. And yeah, hopefully we get a better thing there.
Yeah. The other part that I'm not 100% sure if this will cause, but I think it potentially could, is if this has detection for features like AVX512 support, then if you run AVX512 instructions on a CPU without AVX512, that can actually be processor level undefined behavior, which would be very bad.
I don't know if it would do that, but that is a potential issue.
Yeah.
Actually, on that note, just like before we go to the next topic here, I do just want to point out that we did the stuff around loop factorization. Again, I'm going to announce it earlier than the actual merge, but the last thing to merge is just a little bit of type privacy on some like neural network stuff. But loop factorization is actually working on version 1.12. So thank Oscar a lot for helping with, and also thank Max, who was the one who took up the SciML small grant to take this on. This has been going for probably like 2-3 months now, and we got a valid version here. Just sans a little bit of type privacy. Yeah. Okay. So moving on to the next topic. I think that the next topic is the base splitting refactors, right? So there's been a little bit of movement going on in the ecosystem here. I just wanted to kind of mention a bit of what has been going on, right? So one of the things that you might have seen happening has been, for example, like very specific versions of nonlinear solve, like nonlinear solve and DiffEq were required for a little bit. The reason was because in the very earliest versions of DifferentialEquations.jl, we had steady state DiffEq that was created, right? So it created the ODE solver, and it created the steady state solver, which was like, oh, just an ODE to steady state. That's basically a nonlinear problem. So, but the nonlinear problem of a steady state is just a differential equation that's ran to infinity. So abstract nonlinear problem is also abstract. Abstract nonlinear problem is just a abstract differential equation, right? And so we just rolled with that for 10 years. Of course, you might look at that and just go, oh, they're kind of different. But it turns out that, like the core, like if you call solve or if you call init, those functions would hit this top level dispatch in DiffEq.jl, which would check for all these things like, okay, are your arguments correct and all that, right? Just the same top level, because most of the keyword argument checking, most of the keyword argument checking, most of the problem, checking with traits and everything, they were all the same as the differential equation solver. So why not just do that? Why duplicate code? But then you had some weird consequences, like for example, not nonlinear solve dependent on DiffEq base, nonlinear solve dependent on DiffEq base. So the nonlinear solvers that we use for the root finders inside of the callbacks was actually not from nonlinear solve.jl, because that would be a circular dependency, right? So all this kind of weird stuff that happened from this. And so finally we took the time to do the work to basically just say, we're moving out these solve dispatches so that way it's in nonlinear solve base. So, nonlinear solve base does not depend on DiffEq base. And then anything that's a shared functionality is in SciML base now, right? So like now anything around, these, just kind of want to show the details here because it could be helpful for folks. Like, if you don't have a concrete element type, if you don't have, how do you handle distributions? How do you find out whether your U0 is compatible with the solver, whether you should promote your parameters and all that stuff, right? All the stuff that DiffEq does is now that piece is now in SciML base and then reused by nonlinear solve base. And the reason is then to also reuse it in optimization.jl base and integrals.jl, right? And all these other libraries. Which meant that there were some version-y things as we had the same function in two bases and stuff. And that, I don't think that anything was true. It was just a nightmare to get this right. So there were some versions that don't precompile right. But this is all done except for one last piece, which is today we just did the optimization.jl base breaking change, which is making it so that way optimization.jl, all the solvers are based off of optimization.jl base, right? So now we actually have this structure, right? That SciML base is at the very bottom. Everything depends on that. That's our general, like if everything in SciML should do the same thing, it goes in the SciML base. And then per solver group, you have like DiffEq base, nonlinear solve base, DiffEq base, nonlinear solve base, optimization base, right? Which are these like, shared between all the solvers. And then you have the solver libraries depending on those, right? So we won't have any of this. So for example, one of the issues we had before was optimization.jl. The solvers for optimization.jl all depended on, so like optimization optimizers.jl depended on optimization.jl, not just optimization base.jl. But optimization.jl also had its own solvers. One of them even had a Fortran dependency, and that was brought into every case that you'd use optimization optimizers, or for example. So we fixed it up so that way all of the ecosystems now do the same base stuff, and so you should get a bit more stability around that. So thanks a lot also to Jaden, who helped out a lot with a lot of the work going on there. I don't think that we're quite done or fully happy with all of it. I think one of the things that we want to do as well is like we might want to do a linear solve base and a SciML sensitivity base, where like you have a version that is just like the minimum version that runs, and then you have the version that you're supposed to use, right? So like for example, SciML sensitivity base could just have everything to make something run, and then it can have extensions for every AD package, and then SciML sensitivity.jl then triggers most of those extensions and puts the default algorithm on there, right? The reason to have the lower level is because then you can have a version that builds without enzyme, for example, right? That's not a version we'd ever tell people to use because we default to using enzyme almost every time. But having being allowed to build a binary with a version without enzyme is helpful. And we want to be able to do the same for linear solve base.jl. So that way we can have a version without MKO, even though we are going to force MKO on you almost every real time, right? So those changes are now in. Yay! I don't want to touch the base libraries pretty much ever again.
Unfortunately, I might. I think it is very possible that we will end up deleting DiffEq base and moving all of DiffEq base to OrdinaryDiffEq core.
Not necessarily, because I mean, DiffEq base still has some pieces that are shared to things like sundials.jl, right? So sundials.jl shares the callback setups and things like that, right? Also, OD interface.
Those should probably be in OrdinaryDiffEq core. I'm not fully
but then
convinced
sundials would require OrdinaryDiffEq core.
Yeah, OrdinaryDiffEq core is really like, it basically is just a DiffEq. I think its only dependency is DiffEq base. We've basically just ended up in this scenario where prior to about a month ago, Sundials had this weird thing where it didn't support the normal initializers, but now that it does, basically all of the code in OrdinaryDiffEq, like there's a little bit of OrdinaryDiffEq core that isn't necessary for Sundials, but most of it is.
Yeah. So yeah, I mean, for those who don't know, there's a Sundials v5 change that happened. One of the major changes is that we updated the binary to the latest Sundials binary, right? But since we were going to do a breaking change, we took the time to make it so that way all of the initialization, like the one thing that was different about Sundials was really like all of its initializations had a different syntax because that existed before the whole OrdinaryDiffEq version of initialization, right? Because we built to just use Sundials first, and then our DA stuff came like 3 or 4 years later. But now instead of it having its own, now it uses the same exact syntax as OrdinaryDiffEq's initialization syntax, and also supports the ModelingToolkit initialization interface and everything. So yeah, it pretty much is like almost like it's just a solver built on OrdinaryDiffEq at this point, in a different repo. Yeah, so I think we could probably piece some of these together, but at least for now, DiffEq base is just really small in a different package.
The good news is that this is actually the one direction that's kind of easy to remove the dependency on, because you could basically, it would just be you move all the code into OrdinaryDiffEq core, and within OrdinaryDiffEq core, you alias DiffEq base to OrdinaryDiffEq core, and then it should be a painless upgrade.
Yeah, at is defined in DiffEq base. So if it's in DiffEq base, use the DiffEq base one. If it's not there, then use your new one or whatnot, right? And then that
No, you just make it so that ordinary DiffEq core stops loading DiffEq base. We'll talk about this later, and we might not end up doing it because it might be more annoying than it's worth.
Yeah, I mean these kinds of changes are annoying, not just to other people who have to be like, oh, why my version is bumping, but they're also annoying to us.
Yeah.
They're not the fun work, right? But like at least making it so that we can use the nonlinear solvers independently of the differential equation solvers was kind of required to make it so that way we'd get like correct error messages, and like the nonlinear solvers were throwing error messages around the function syntax of the ODE solvers because it was using the ODE solvers solve code, right? So kind of just need to be like, all right, like that needs to separate.
Symbolic indexing is also going to be happier because there's a little bit of jank there around nonlinear problem subtyping DE problem, and then you need to say like DE problem is time dependent, but nonlinear problem isn't. But steady state problem is its own sort of weird thing, and then it ends up really weird.
Yeah. Not abstract nonlinear problem being being an abstract differential equation problem is just, if we had the foresight in 2016, I would have never put that. But that's the kind of thing where if it's in there long enough, there's some pieces of the system that just start making the assumption that it's there. And it takes like a month to just root all of those things out. It's like, oh, this dispatch actually exists because it's hitting abstract DE problem, right? Yeah.
It's one of those where SciML really started out as a stochastic DiffEq solver, and then it's kind of built down. Whereas the sensible approach, obviously, would be to build up to the fancy things, but that wasn't where it was needed first. So that's not what we did.
Yeah, I mean, it started. We called ourselves Julia DiffEq for the first, 5 years or so, right? So the idea of everything's a differential equation solver made sense until it didn't make sense.
On the topic of moving code around, though, is there any plan to like move what's it called, delayed DiffEq into OrdinaryDiffEq? Because it's a lot of very weird like internal stuff there.
Yeah, delayed DiffEq and stochastic DiffEq shouldn't be different repos at this point. They should be repos on OrdinaryDiffEq. I mean, this is something where
it's actually an easy move.
Yeah, those moves aren't that hard, and I don't think that anyone will be able to notice that move, but that'll be a move that we'll need to do in the next month or two. Fingers crossed it'll be the kind of, no one will notice kind of move.
Yeah.
I mean, it kind of ruins your Git history, right? Because you lose some history there or whatnot. But
and boundary value DiffEq mostly can stay on its own, I think. But
boundary DiffEq is its own whole world, right? But stochastic DiffEq, for example, I mean, when it says, I'm going to create a Jacobian, it calls ordinary DiffEq's Jacobian code, right? And so, everything that it does, other than adding its own time steppers, right? It's just reusing a lot of the same base ordinary DiffEq code. So it's
specifically, it's using this sort of base ordinary DiffEq code that really has no interface and is horrible. And I really want to correct it out.
It's pure impingement.
A lot of this I have to that was because it exists in a separate repo now. So hopefully we'll be able to clean this up.
Yeah, so that'll be coming. We'll get back to that topic at the end here. I think that the other topic we want to touch on is the huge amount of changes that are going on in the symbolic space, right? With the SymbolicUtils v4 change. So I guess Aayush, you want to take say a summary on that?
Yeah, sure. So as Chris mentioned, like SymbolicUtils v4 is it's actually out now, and then that's a very major rewrite of SymbolicUtils, and then it's
hidden items.
Oh yeah, there's a lot of them, and these aren't comments either; they're all commits. But yes, so this will eventually propagate its way up to ModelingToolkit, and and the idea here for all of these changes really is to make it so that SymbolicUtils, being the very low-level symbolic manipulation library, is type stable, or as type stable as it can be, because it inherently represents some dynamic behavior. And the reason we want that is so that we can precompile our symbolic workflows. Because if you ever if you currently you load ModelingToolkit and you try and simplify an OD system, it's gonna take a bit for the first call, even though we actually try and precompile what we can. Just because currently nothing with respect to symbolic manipulation actually is type stable at all. It just gives up and goes into any And so and then because we're doing a breaking change, there's a lot more stuff in there. So it includes like first class support for arrays. So this exact array of syntax is now supported, and we implement like a primitive array algebra, and there's a lot less type piracy happening in Symbolics. So that SymbolicUtils is the one defining all of the really low level methods for this. And as of right now, I think like Symbolics is also almost updated. The caveat there is like we've chosen to like optimize a few specific algorithms that we know people use very commonly, because Symbolics is a very large package, and making 100% the package type stable is going to be several more months of work. And then, of course, then Modeling Toolkit builds upon that, and Modeling Toolkit is going to be type stable. So the idea is that when you simplify a system, it just precompiles and it doesn't take another 30 seconds.
Yeah, so let me kind of just give a little bit of a primer, so that way people get a feel for what's going on in this library, and why this is what was a change, what this is all mean, and then everything, right? I think when people think about like a symbolic expression, right, they think like, oh, I have a tree, right? You have x plus y is the tree of plus as the operation, and x and comma y is the two things in that tree, right? And you then have trees of trees, right? Turns out that is the representation of functions that you have in, say, Julia's AST representation. But it's not actually always a good representation for symbolic computing, right? Because in this, one thing that comes up, for example, is what we call like add mul here, right? Or you might want to say, oh, I have a dictionary of the terms in here, because I might have x plus y plus z. X plus y plus z is equal to y plus x plus z, and like all the additive commutative rule, associative commutative rules, right? And so if you want to be able to check that two symbolic expressions are the same, if you put them in a dictionary, you just have to check, like hash check, are they the same? So if you have them as like a tree form, like as an array, you have to check all orderings. And of course, orderings blow up exponentially, right? And so then you want to start to be able to say, okay, if I'm building a polynomial, right, then I want to be this add mul thing. But then, if you say like, oh, I have sine of x, then I want to be like, sine of x comma y, then I want to build a tree with x comma plus y. Or I want to be a tree of a term on top of a polynomial, and I want to have the symbol, right? And so you have all these different, to actually optimally do symbolic computing, you want to have a few different representations for different things that you run into that are specialized around, are they associative, commutative, and what other rules can I apply, right? So you want to have all these different types, but then you want to be able to say, oh, like, for example, my tree type is I have a function, and then I have an array of symbolics, right? But if your symbolics are all different types, then what do, right? Before, what we do is we just say, that's an array of anything, right? So we'd have all of these like small vector of anything kind of arguments, right? And that's what made symbolics type unstable. But it was still, even though it's type unstable, it was still so much faster to just like have it be like specialized in polynomials, like orders of magnitude, right? So it just made sense to continue that, right? But where we ran into issues was things like precompilation and such would break, right? And so Aayush has now turned it into this representation. So this representation, you can see that this is kind of like a non-standard Julia thing, right? This is a Moshi, right? So it's a Moshi summed data type. So what we have here is, it basically is, you have one type that has these different representations. So the what you get is a type that has a union of all of these different fields. But then it can kind of act like it's a term, act like it's a sim, act like it's a const, but it's a runtime check for which of these that it is. So it's actually type stable to have arrays of all these different versions. And then, so if you have an array op and you have a div or an admul, a polynomial together inside of the same array, that is type stable, because that is just an array of basic symbolic implies, right? And that's how all these are now type stable. And then that means that since the very bottom of Symbolics is now type stable, it's all type, we're able to start building it type stable all the way up. And one of the major changes here is also making the array operations also part of everything here. Right? They were own type before, so anything that could have an array, a symbolic array, suddenly that had even more form of type instability before. Now, one of the things that we also do here is also like x plus 1. 1 is a symbolic constant of 1, right? Where that can be, it basically is boxing it so that way you can always treat x plus 1 as a symbolic and a symbolic together, right? So this is a little bit different from the representation that we had before. Most things should be completely the same. Most things should be faster because type stability, you get a lot less dynamism, a lot less dispatch. But there are some trade-offs here, right? Ayush, you might want to go through maybe some of the trade-offs and some of the differences in behavior that we have to put up with this.
Yeah, I think there are like two really big differences that people are going to notice. So first of all, if you ever looked at the basic symbolic type that we had before, you would see it looked something like basic symbolic of real, and if you created an array, then it would be basic symbolic of vector real, for example. And that was also one of the reasons it was type unstable, because you can have a function that takes an array and returns a scalar, and then you can't store in a type stable manner what the types of all of the arguments are. So if if you were dispatching, for example, on something being a real symbolic value, or a symbolic value that represents a real number, that's just not going to work anymore. And this is exactly why, that we just simply can't store it in a type stable manner. That doesn't mean that we don't have that tag anywhere. We still store the tag for what type is this. We just don't put it as part of the type of the symbolic. So like sim here, for example, has a const type : type t. And the second major change is just going to be const, because if you had like, if you did x minus x prior to v4, you would get 0. You would like actually get an integer 0. And right now, after these changes, you'll get a const 0. And just to make sure that it's really obvious, we print it in blue. So if you get a blue 0, it's something that's wrapped in a symbolic variable. And this makes it so that any operation that you do on a symbolic variable will return another symbolic variable. And that is essentially the basis of our type stability, because you can statically infer that if I add two symbolics, or if I multiply two symbolics, I'm going to get a symbolic out. I'm not going to get a number, or I'm not going to get an array or something else. So yeah, those are the really, really big things that are just very visible and will break the most amount of code.
Yeah, and then so if you actually do want a number, you have to ask for a number. And I think that's pretty around the ecosystem as well, right? So like another case of that is like one cool little kind of, I think we had a feature for a while with some substitute, right? Where if you did substitute, where you just said, oh, x is a number and y is a number, it would basically like interpret the code and spit out a number, right? The way that worked was that it just kind of assumed that symbolic plus a number is always just it could give you the number, right? X minus x is 0, kind of thing, right? But now, since these things are all numbers, you have to actually turn on an argument, right? You have to do like val of true if you want something to actually give you out a number. Otherwise, they'll just substitute in the values, right?
Yeah. And like, I guess the reason for that then is that if you have x plus y and you substitute x for a number or y for a number, then doing so is dynamic dispatch, because it's a runtime check for whether you've substituted both of the values or not, and that just makes the entire thing slow.
And just to be clear, if you do have like x plus y substitute at x equals 4, y equals 6, will the result of that be a basic symbolic const 10, or will it be basic symbolic const 4 plus basic symbolic const 6?
It'll be basic symbolic 10.
Yeah. And then you just have to really say, okay, now give me the number out.
Yes. And the reason we still fold those is because you really, really want a canonical representation for anything. You don't want the same thing to be represented in two ways, because there's like, the reason this is a 3700 line file is because there's a lot of edge cases where, what if I'm multiplying a division term with a multiplication term with an addition term with something that takes in an array, and then you need to reduce it all down to canonical form, so that you know that any of the arguments that I'm getting are in this canonical form. Otherwise, it's a very combinatorial explosion of the different edge cases you have to handle. So yes, we do a little bit of type unstable things, but it's for a very good reason, and it's all very isolated.
Well, like, do we actually have the fact that you'll always be able to canonicalize uniquely? That seems like that would be Turing complete.
I think we do get the canonicalization because things that have all these different rules, right, for like associative and commutativity, we put them in these dictionaries, and the dictionaries on ordered, right? And so then it has like just the hash lexicographical ordering, right? And so because
the thing I'm thinking of is like, if you write like sine squared x and cosquared x, or like sine squared x plus 0.5 and cosquared x minus 0.5.
Okay,
That
yeah, you can construct, yeah.
Right.
Yeah. So that won't turn into 0 because this only assumes the basic rules of scalar algebra and a little bit of
Okay.
yeah. So it's not gonna like identify sine square x plus cosine square x. What it is going to do is say that if you're multiplying 2x and 3y, it's going to store it in a dictionary where the keys are x and y and the values are 2 and 3, instead of the keys being 2x and 3y and the values are 1 and 1. And then if you're like, the really painful edge case here, for example, is if you're multiplying a list of scalars and then there are some arrays in between, you want to move the scalars up ahead, you want to multiply the arrays, and you want to store the arrays in an ordered manner because array operations are not, array multiplication is not commutative. And then you want to store it in a standard form where, if I want the scalar part of this entire multiplication, I look here.
Yeah. And speaking of some of the array stuff, right? So not only did we move the array off to also be a part of the general type here for what a symbolic is and everything, right? We also did get a new feature on it, right? We have symbolic arrays with undefined size, right? Which is something I think a lot of people have been asking for.
Yes. So, yeah. So, symbolic arrays can have an undefined size, and we just do whatever validation we can. So if you're multiplying two arrays, we'll make sure that both of them are matrices, or it's a matrix and a vector. And then if you like try and generate code for this, so if you're generating code for, say, adding 1 to each element of an array, we just loop over the size x comma 1 and size x comma 2, or like 1 to that, or axes x comma 1 and axes x comma 2. And so the idea is for like PDs, for example, eventually you should be able to just say that this is the size of my discretization and run a loop over whatever size my matrix is.
Yeah, so we can compile a PDE code in O of 1, right? That works for all sizes of your PD discretization. So if you change your PD discretization, right, you still actually can use the same generated code, which is that should make it. Yeah, that should make a lot of things like method of lines.jl. So once we get a method of lines.jl up and running with this, like it should change some of these long compile times down to just a small constant. That'll be a huge win. So yeah, and then one of the other, and then following up on this, Darius is starting to do a lot of work where he's setting it up with like bumper and reactant.jl, right? So that way, if you generate code with array operations, it should be non-allocating and fast and all that. So yeah, so Symbolics.jl and ModelingToolkit.jl in general is always like, if you have a really big equations with arrays, the code, scalarize it. I think this new underpinning gives us the tools to build the solution, and then we have some code gen things already there at O of 1. There's still some more work that needs to be done to make all of the code gen better, non-allocating and all that. And there's some work that needs to be done on the modeling toolkit side, so that way some of its analyses don't scalarize. But we're pretty close to this nirvana of allowing you to build a model with undefined sized arrays and then like let it just build a for loop.
There's also putting all of this these array operations here also lets us eventually do cool things like loop fusion. So if you have like multiply matrix A with matrix B and then multiply matrix A with matrix C, we can eventually just figure out how to turn it into A into B plus C. And then if there's a lot of like these weird nested like non-standard array operations, there's analyses we can do to just reduce the number of times you're looping over the same code.
Yeah, and so the array operations are generally written with this, add array op, and which is a Tulio-like syntax for, at a symbolic level storing like this, Einstein summation, which we could have, future GSOC students or something work on an array compiler that improves this. But the other thing too is like, during the code gen, we can just have a flip that, flip it on to use reactant, and reactant should be able to do a lot of these in the code gen stage as well. So we can get a version of this at the LLVM level very soon, but then be able to propagate up higher level ones as well, because the higher level ones should actually improve some derivative roles and things like that. So it'd be good to have them. So this kind of was like a really nice kind of the array stuff is kind of, it wasn't something that was kind of considered at first as part of this major change, but it was almost like, enabled, like, hey, if we're going to be changing the array representation right now, let's make sure we can do undefined size arrays. And the code gen around that should be O1 too, right? Like, it kind of just fell into the place of like, oh, right now it's time to do any breaking change. We need to make that work, right? So I think that's that. I think that the last thing here is everything that's going on for OrdinaryDiffEq v7 and DifferentialEquations.jl v8, right? I want to kind of mention a little bit of this, right? So there's some discussions with the community, just like where are we going with all this, right? The key thing is, so for folks who haven't seen this big issue, kind of got some ideas from the community and kind of found a direction that I'm happy with to just start rolling with, right? The idea of what we're going to do is, so DifferentialEquations.jl necessarily depended on everything, which ended up not being so useful the moment we got big, right? Because like the number of people who are solving a stochastic differential equation, a boundary value problem, and a DAE in the same session is zero, right? So everyone started wanting to use all the little sub libraries, right? But then it's like, oh, if you want to use a sub library, well, why does differentialEquations.jl have everything as a dependency? A, because its battery is included, and as a design choice, and then B, it had the default algorithms, right? And the default algorithm necessarily needs to depend on everything it's going to default to, right? And for a long time, that also had to require a lot of different libraries, because they're like, oh, the best solver for this kind of problems in OrdinaryDiffEq, but the best solver for this kind of problem is sundials, right? Or, some binary, right? We've now pretty much hit a point where in all of our benchmarks, it's like the best algorithm is something that's in pure Julia. And so, you're like, okay, all the defaults for ODEs is OrdinaryDiffEq. All the default stochastic differential equations are stochastic. And pretty much we have winning libraries at this point. The ones that we've really spent the most, the core solvers of SciML are just winning on all the benchmarks.
And this would be a great GSOC student project if someone wants it. Is for DAEs. Our best solver is still IDA from Sundials. And we have a solver called DFBDF that's often better than IDA, but it's missing about half of the features that we need to support the full SciML interface. So someone
missing one specific Jacobian optimization, like it just doesn't reuse a full Jacobian in a specific spot.
That's one of the issues. It also is missing callback support, I think.
There's callback support in there. I did that earlier this year.
Oh, great. And I think it has some interpolation weirdness.
Yes. Okay. FBDF and DFBDF both need to have interpolations based off the collocation polynomial. Right now they use Hermite polynomials, which is not as stable. Yeah. So okay. So two pieces. Yeah, and then but so you would still kind of point people to use IDA if you're just going to use DAE problem instead. But A, you should almost always use the mass matrix ODE. It's just like every benchmark shows that those are faster and more robust, right? And then B, yeah, and well, even the one where the DAE problem does better than the MTK generated code. The reason is because the MTK generated code always uses a diagonal, semi-explicit mass matrix. If you use a
non-diagonal semi-explicit faster.
Exactly. Yeah. So you just have, if you hard code that non-diagonal mass matrix, it's actually better in that case to still use the ODE problem form. So yeah, but ModelingToolkit doesn't know how to code gen to that. So that's like a more of a ModelingToolkit issue. But yeah. So so DAE problem, we do want to kind of finish up that solver. It's, we'll make the default algorithm be the DFBDF early, but still to mention in the docs that IDA for this property. And hopefully in the next summer, we'll do those last few optimizations. I mean, we kind of know exactly where they are. So it's not the hardest problem. It's just more about getting the time for that. But yeah, so then, with all those different changes, then the defaults for steady state problem move to steady state DiffEq. The default for ODEs and DAEs moves to OrdinaryDiffEq. The defaults for DDs moves to DD delayed DiffEq. The one last thing we have to do is the defaults for SDs and our ODEs moves to stochastic DiffEq, right? And then suddenly or DifferentialEquations.jl is no longer even has any code, right? It's not a default system anymore. And then the question is, what does DifferentialEquations.jl for? Well, the idea here is let's just make it be the package that you go to for ODEs, because most people think about it as the ODEs in the first place, right? Cut everything else out of there. Just make it so that way it does the default ODE solve with just the few solvers that 99% of people use, right? So the 6 solvers that end up in the default algorithm. Cut everything else out, and then it should load pretty fast, right? And then
We'll probably also keep like DiffEq callbacks in it.
yeah, maybe a few things like if you could call back, so that way it's just simple, nice to use or whatnot. But then then the documentation's actually already been updated, right? So DiffEq.SciML.ai, you go there, you'll see that, for example, if you go to like the stochastic DiffEq documentation, we're already priming everyone that like in the SDE version of the docs, you tell you use stochastic DiffEq, right? And then you go to the other ones, and it's like, oh yeah, import delay DiffEq, right? So this one I still think has differential equations for one reason, right? So we're still kind of finishing this up, but yeah, we're trying to push everyone to like just use the specific package and trying to fix the documentation to that. And then we'll make the bump to then just say differential equations is just the ODEs. And it's also just the simple ODEs. It doesn't have every solver. Here's a subset of solvers that it has. And if you want the rest of the solvers, here's all the specific sub packages you load, right? So right now, these are all things in part of DifferentialEquations.jl and OrdinaryDiffEq by default. But soon we'll start to be able to do this part where we say, okay, if you want these solvers, load this sub package. If you want these solvers, load this sub package, right? Which is details for people who are very detail oriented, because we know from the statistics, 90.999% of people probably use the same 10 solvers. So, the rest of the long tail doesn't need to be loaded every time.
And the other advantage is that this way, we can switch out which solvers those are when people, or when we develop new, better solvers. So there's still a lot of people that are using Rotos 5, for example, even though Rotos 5P is the new, better version of it.
Yeah, and there's a few other things that are going into the OrdinaryDiffEq v7, right? Because we're going to try to just make sure we do the OrdinaryDiffEq v7, which trims out all the other extra solvers from the main OrdinaryDiffEq at the same time that we trim from DifferentialEquations.jl, right? But then I think that there's a few other things we want to get into there, right? So Oscar, you wanted to do something around preconditioner interfaces, right?
Yeah.
And that has a linear solve bit as well.
I think I want to talk about the preconditioner interface a little bit, because this is a change I'm pretty excited about. Basically, it previously in linear solve, nonlinear solve, and OrdinaryDiffEq, if you wanted to specify a preconditioner, the preconditioner was an argument to solve. Whereas now in linear solve and nonlinear solve, the preconditioner can now go as an argument to your lin solve argument of the solver. The reason why this is better is because it makes it a lot easier to switch out what the solver looks like, and it makes it so that you can save the preconditioners more easily after you've built them. And so this change is going to be bringing this up to OrdinaryDiffEq as well. And while we're at it, whereas the OrdinaryDiffEq has a very complicated lin solve interface currently, whereas now we're using this new version uses the fact that you can pass parameters to a linear problem. So if you wish to use extra data in your preconditioner, such as like your time step or something like that, you can pass that in custom. But for everyone else that isn't using a really weird preconditioner like that, they don't have to write a complicated preconditioner, and they can just use like IOU0 or Algebraic multigrid without any customization is the goal here.
Yeah, so that'll be a nice improvement when it comes along. And again, like that has to fit into some breaking change. So if we're going to do this break for all the trimming, making dependencies linear and everything, now is the time to clean up some of our of those interfaces. I think the other one that we have this PR changing here, which is that to just always check it by default. Which again, like sundials.jl v5, it already set checking it as a default, right? And then we'll do that here. So if you're using ModelingToolkit, it always runs on ModelingToolkit's standard initialization, right? But if you're just writing a standard DAE, it won't just change any values for you. It will always check it by default. You have to tell it, hey, you're allowed to change my initial condition, or you're allowed to change my algebraic variables, or you're allowed to change all my variables, right? Which will be a nice change, because a lot of people, the way that this interacts with callbacks, always going to confuse some folks.
The other part of it that's very nice is currently OrdinaryDiffEq Rosenbrock is in a very weird spot, because the Rosenbrock solvers don't rely on nonlinear solvers for anything other than running the initialization. Whereas this way, if you load the initialization, that's the thing that loads the nonlinear solver, and therefore no one else needs to be responsible. Like OrdinaryDiffEq Rosenbrock isn't responsible for loading a nonlinear solver that it's not going to use.
Yeah, so like, Catalyst users of just ODEs, they will get the Rosenbrock solvers will get a even faster loading than they have right now. Then make default trim controller trim compatible. So like last little details of interface changes that were dynamic before, that now need to just instead of just saying true or false, something, making something type level information, that way it's trim compatible. We'll shove those into that same breaking change, so that way, again, to get the whole ecosystem trim compatible. And then I think that there was one question that we had before at the beginning of the year, which was, should we default to a forward diff to odd enzyme? And I put the check mark there because I think the answer is pretty definitively no. And I think that the answer became no because we saw how long it took for version 1.12 or 1.11 to support enzyme. And then the answer is just like, yeah, we can't just not have, OrdinaryDiffEq not working for 6 months, right? So we'll still default to, it's very easy to tell the ODE solver to use enzyme as the automatic differentiation, but we just, defaulting a forward diff means that we always support day one on new Julia releases, and that's just too strong of a property to give up, right? Mooncake and enzyme just cannot guarantee that behavior. So, and then the only other thing that I think that is still a major question mark in the major change here is, will we get the nonlinear solvers to be good enough that we delete the internal nonlinear solvers of the OrdinaryDiffEq and just always use nonlinear solve as the nonlinear solvers of the differential equation solver as well? I think Oscar's tasked to try to see if we can get that done in the next month or two. And so there's stuff going along of can we get this fast enough? And so you'll see movement going around and nonlinear solve and everything. That's what we're trying to do. We're just trying to see because the thing that you have to do inside of an ODE solver is very particular. And so that's just a question of, can we get that fast enough? So that way we can get rid of OrdinaryDiffEq having its own nonlinear solver. And if you saw my JuliaCon talk, right, things like my JuliaCon talk and some new research features and everything are building on this feature. So we want it to be fast anyways. But just also win if we could just delete the other version of the nonlinear solvers too.
The OrdinaryDiffEq differentiation and OrdinaryDiffEq nonlinear solve are my two least favorite parts by far of OrdinaryDiffEq currently. So being able to delete a lot more of them would be very nice.
Yeah, it's that kind of piece of code where you go, man, I don't want to have a different nonlinear solver. It's like I understand. I know why. I mean, I of course I know why there's a different nonlinear solver in OrdinaryDiffEq, right? But like, it feels so bad to then spend nonlinear solve 3 years building that up, and then just to say, well, we can't use inside of OrdinaryDiffEq because you need to have these special hooks and everything, and you're just like, well. But if you could use ModelingToolkit.jl, then you also just get a better nonlinear solver because it has all these trust region methods and all these line searches, yada yada, and so you'll just be able to make bigger time steps because it just converged better. But it's like, but you can't use this library because even in its basic mode, it's slower because it can't do these specific things. It just feels bad. I'm hoping that this also ends up in the V7 because I don't think that there's no other planned break anytime soon. So if it's not in the V7, then it would kind of never become the default. So
yeah, the good news is I'm not actually sure that it's a breaking change. We'll see.
Yeah, we'll see. I mean, I don't think it is a breaking change, right? Because exactly how we do the nonlinear solving is a kind of detail under the hood. But it does change enough that you kind of want to put it in with a breaking change. Because
that makes sense.
Your floating point values on every time step will be different for every implicit solver, right? It's a sweep.
That's true. Anyways, like we make also like that can change just from Julia version to Julia version, or just from like computer to computer,
Yeah,
your
you can
blocks
change
are
on your
different.
different CPU. Yeah, which different blocks you have. Yeah, we don't guarantee that, but it's sweeping enough of a change that it feels nicer
Yeah,
to include.
that's fair. And actually, if possible, we'll see. I might try to couple this with some changes to how you specify your derivatives. So currently you can specify Jacobians and W operators and VJPs and JVPs, but the version of it that you specify and the place that you specify it isn't really where I want it to be, especially now that we have differentiation interface as a very nice autodiff library. So it's possible that the actual breaking part of this change will be um, more in how you specify what derivatives you can provide to the solver. But if possible, we would like to make it as non-breaking as possible.
Fingers crossed. Fingers crossed that like in a month or so, like we just go, yeah, now we deleted half the OrdinaryDiffEq nominator solve half of its code because just using modelingToolkit.jl. And then that's just like a free feature of the DifferentialEquations.jl bump. So I think that's everything. Anything else anyone want to bring up on these topics? Cool. If there's nothing else, I just want to close out and say, we'll try to, we'll generate transcripts from this, generate a blog post or whatnot, and throw this out on the Julia Lang YouTube. And, if people want to hear more of these dev chats, we'll definitely be pulling other people in from the SciML space and talk about, things going on and, some of the stuff that Torkel's doing with Catalyst and some of the stuff that's going on with, the verbosity chain, the new verbosity system and logging system that Jaden's been doing. And, like just pull in different parts just so that way people can kind of get, dev updates. I know you get to hear them at every JuliaCon, but that comes once a year. And again, it's a lot of work to come up with slides. It's much easier just to be like, yeah, you want to know what's happening? Here's the pull request, right? So this is our lazy way of sharing more information. So if you like it, thumbs up and everything, and we'll keep on doing them. Other than that, thank you, everyone. I think I had a lot of fun.
Yep.
Absolutely.
See you later.